All right, the last section the last part of section 2.2 is here. The continuity correction is a topic that's beyond the AP curriculum, kind of. It's really easy, and I think it's kind of important, but we'll leave it to the end of the video if we have time. Assessing normality. It's a little more of a important issue, I guess. We can pretty much find any probability we want for normal distribution. We did a lot of examples of how we can calculate all kinds of probabilities with a normal distribution. But using a normal curve to find probabilities is only helpful if the actual distribution is normal or is approximately normal. First of all, let me just point out that no real data set is going to be exactly normal. They might be close to normal, or normal calculations may model it pretty well, but nothing's going to be perfectly normal. So is it close enough, I guess, is a real question. Also, many of the analysis procedures we learn later in the year will only work if the data comes from a distribution that's approximately normal. So for these reasons, it's important to be able to determine if a data set is approximately normal or if a sample comes from a population that is approximately normal. And by the way, this is an even more complex question. So there are two ways to assess normality. The first one is to create a graphical display like a dot plot or a histogram or something like that, and just see if it looks normal. Is it clearly skewed? Then it's not. Has more than one mode, bimodal? Then it's not. Or if it isn't mound shaped, then it obviously isn't a normal. If it kind of looks normal, then maybe it kind of is. Another way to do it is to create this plot called a normal probability plot and use it to assess normality. So that's what I want to talk about here right now. A normal probability plot is a difficult graph to explain, but it's not beyond the scope of this class. It's actually not that complex, but it is very time consuming to make. If you want to see how it's made, come by after school. I can show you, but that's not really the big issue. The big issue is how to interpret it. So if the plots on a normal probability plot lie close to a straight line, then the data set is approximately normal. So if this plot is linear, then your data set is close to normal. Systematic deviations from a straight line indicate a non-normal distribution. That's pretty much it. Here's an example. This data set looks approximately unimodal and symmetric, close to it, right? And as you can see, the normal probability plot is close to straight as well. The little deviations here, little wiggles, a couple points off a little bit, but that's not unusual in a normal probability plot. Whereas this distribution that's skewed to the right, as you can see, it has significant curvature from being linear. So if you see something like this, you know it is not normal. You see something like this, you say, yeah, it's pretty close to normal. These were done by your Inspire calculator. These are done with Minitab. Minitab does have these fancy little tolerance bars that kind of says, well, if your data points are inside there, then it's kind of normal, and if they kind of get outside there, then they're not. But same graph. Open the class survey data on your calculator. Create normal probability plots of heights. So let's assess the normality of heights, shoe size, cash, and miles from school. You should have this on your calculator. Open it up. We've looked at the data set before. I'm basically going to show you guys the last numerical plot that your calculator does. So let's start with height. And we've talked about this before, it kind of looks unimodal symmetric. I don't know. I think some of these might have been some people doing some calculations. I think this 5'6" was supposed to be 5'6" inches, not 56 inches, but whatever. So let's take a look at the normal probability plot. Menu, plot type. So we've talked about dot plots, box plots, histograms. There's our normal probability plot. So what do you guys think? Does it look pretty normal or pretty straight? Little deviations here, kind of a couple deviations here, but for the most part, pretty straight. So I'd say, yeah, that seems, I have no evidence that it's not normal, so I guess it's pretty close to normal. I will point out to you that this distribution isn't really normal. If we were to add gender here, I think we'll see that there's actually kind of a bimodal tendency in this height data, but the peaks are so close and there's so much overlap that whenever you don't have gender, you don't really see it. So let's take a look at some other ones. Let's start with the normal probability plot, so we don't give it away ahead of time. So let's take a look at cash. So as you can see, this data set is very much so not, this plot is not linear at all, indicating the cache is not linear. I also wanted to point out, this isn't real easy to understand, but, and I'm not even sure if I wrote, this is me writing it, so you know that's maybe a little bit questionable, but when you examine a normal probability plot to look for departures from linearity, don't overreact to minor wiggles. I guess I just said that. To determine if a distribution is skewed left or skewed right from a normal probability plot, draw a line through the main body of the data points. If the points that deviate from this line are to the top right, then it's skewed to the right. And if the points are to the, so that's kind of, what I mean by that is like right here is your main data, most of your data is kind of in here, and the points that deviate from it are kind of to the top right. Basically, these are more spread out than where you would expect them if it was a normal curve. That means this distribution is skewed to the right, and you guys already know that. I mean, cash on hand, remember how crazy skewed it was? Let's take a look at, what was some of the other ones? I think distance from school, distance. And again, this is another skewed right distribution, but our main data is here, certainly significantly curved. This is not normal. Nowhere near it. Do we have another data set that was approximately normal? What was the other one I asked you to look at? Shoe size. Shoe size. That should be kind of close to normal, I think. Again, this is pretty close to normal. We got a little bit of curvature here, a little bit of curvature there. But I'd say that follows the linear pattern, so I'd say yes to normal, or approximately normal. Let's take a look at the dot plot. This one doesn't separate quite as much when you go by gender. Well, I guess it still does. I think women's shoes kind of run a little bit different size, so I thought that maybe tightened up a little bit, but perhaps not. Is there any other numerical data set that was interesting for us to look at? Hours spent on homework, on average hours spent on homework per week. Oh crap, wanted to see the normal probability plot first. This one's a little bit, it's not quite so skewed, but there's still significant curvature down here and kind of up here. Yeah, that is skewed to the right. I don't really have a skewed left distribution, unfortunately, to see what that looks like. Yeah, so. Oh, enjoy math. Let's take a look at that one. Rate your enjoyment in math on a scale of 1 to 5. That's not really, is that even numerical? Nah, let's not even look at it. Okay. So that's it for chapter 2. Okay. Since I am only at about 8 minutes on this video, I am going to come back and show you this continuity correction. It's kind of a prime candidate for a bonus on a test, so, and it's easy, so maybe it's worth your time to look at. When using a continuous distribution to approximate a discrete measure, we can use what's called a continuity correction. Let's look at an example. Tiger Woods' drives are approximately normally distributed with an average of 304 and a standard deviation of 8. Let x equal the length of a drive by Tiger Woods. It's a random variable. Whenever he hits the ball, we don't know how far it's going to go. Find the following probability using the normal curve without a continuity correction. Okay, so what is the probability that he hits a drive exactly 300 yards? So let's draw it. The mean is 304. Standard deviation, what was it, 6? 8. And if I want to know the probability that it hits it exactly 300, it's going to be right around here. But again, what's the area underneath a single point? It's 0. This is 300.000000000 to infinity. The probability he hits one exactly 300, if you measure with that kind of accuracy, is nil. But that's not really what we mean when we say what's the probability he drives at 300 yards. To use the continuity correction, we recognize that drive lengths are rounded to the nearest yard. The PGA rounds to the nearest yard. They don't measure that accurately. So the PGA would record a drive of length 300.347 blah, 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 blah. They would record that as a 300-yard drive. So if we want to find the probability of a drive going 300 yards in this discrete measuring system, we need to find all the distances that would round to 300 yards. So basically, a drive would be counted as 300 yards as long as it's bigger than 290.5 and smaller than 300.5. So basically, all of the drives from 290.5 to 300.5, all of these would round to 300 and therefore be recorded as 300. It's basically a correction for using a continuous distribution to model something that people measure discretely. Menu, statistics, distributions, normal CDF. I want to go from 290.5 to 300.5. I think the mean was 304. The standard deviation was 8. Gosh, that looks, 290.5, my bad. Did I write that down on the page too? This isn't 290, this is 299.5, my bad. Those are the values that would round to 300. Oopsie. Let's fix that. 299.5. So about 4%, 4.4%. 0.044 or 4.4%. So about 4% of his drives are going to round to 300. And then you could find any single value by just kind of taking this band of all the numbers that would round to whatever that value is. Okay? And if you wanted to find a range of values, like the probability that he drives, that he hits a drive over 300 or between let's say between 290 and 310, let's say. Well, to do that, then I would round this one down. Then I would round this one up. It just gives you a slightly more accurate, sensible estimate for whatever you're trying to calculate. Okay? Very easy. All right. Good luck.